Ladies and gentlemen, hello and welcome. Coming to you once again, not quite live from One Take Studios. Today's topic is estimating P in the binomial distribution. I'm going to be referencing some thoughts that we've had recently about finding mu in a distribution where we either do know sigma or do not know sigma, because there's a lot of similarities here. All right, I'm going to do some compare and contrast. So today we are estimating P in the binomial distribution, and I think it's important to go back through and review some of our key variables for this. All right, so binomial, that means two outcomes, yes? We talked about P being the probability for success and Q being the probability for failure. So those things are still in effect. We're going to use those. I am going to kind of throw one more word right here, though, is that often when we start talking about estimating P, they use the word proportion, instead of probability. So you may see something that represents P as the proportion of success. That's going to be the same thing. It's the same P that we know and love from other binomial work. All right, so the probability or proportion of success, and then Q is for failure. Other things that we know or need to know, N is going to be our number of trials. That's been pretty standard. And then we have R. Now some people struggle with this one. R is the number of successes. P is the probability of success, R is the number of successes. So this is saying I've got 5 successes out of 20, that type of thing. All right, and then actually using 5 out of 20, that would be your probability. And dun dun dun. See, here's the thing, we don't talk a lot about P hat usually, but P hat is the point estimate for mu. In other words, we don't actually know the entire population for this thing, but we are looking to estimate this probability regardless of the fact that we don't know the population. But if we can get an estimate, we can base our estimation for the population value based on the sample statistic. And so P hat here is kind of like X bar is for mu. All right, this is based on our sample numbers. Here's the probability / proportion that we've seen thus far, and we're going to use this as the basis for our estimation for what P would be. All right, what else do we have here? All right, so what we are acknowledging then is that we are doing an estimate. However, there will be amount of error. There is a really good chance that the P hat that we stumble upon with our sample is not going to match the true population proportion, and there will be a difference between them. This is not a calculation formula, this is just a conceptual idea, understanding that we're going to be off, and how much we are off would be considered our margin of error. As before, we do have a formula for the maximal margin of error, and this is going to be important. Ladies and gentlemen, please make sure that you can find this in your notes someplace. Woo, there we go. There we go. All right, and this idea that E is going to be our maximal margin of error, we have Z sub C again. If you'll remember, this is called a critical value. This is still a Z-score, and it's associated with the C here is going to be the confidence interval that we are looking for. All right, so we're still looking to be a certain amount % confident, and this is the Z-score associated with this. So Z sub C is our critical value. And then this time we don't have sigma or X bar, so instead the other portion of this is times the square root of, and we've got P times Q over N. So this is going to be our formula. This is what we're going to see for calculation purposes, not this guy right here. All right, so Z sub C equals the square root of PQ over N, which means another big idea then overall that we are going to see is this. Dun 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 dun. This is the overall structure of what we have going on here. This idea that I'm looking for an estimate for P. The estimate is an interval. Again, we're not going to say the estimate is 26%. We are going to say that there's an interval going on here, and I can find that interval by using P hat as the estimate. And if I do P hat plus my margin of error, there's the high end of the interval. And if I do P hat minus the margin of error, there's the low end of my interval. And then we are a certain amount confident that our proportion is truly between those values. So a ton of similarity to the work that we have seen working with finding mu and estimates for mu. All right, now I want to kind of walk through a full example here to show you what's going on, and I made this up. It's not like, completely made up because I've taught for many years, and so I think this is at least somewhat realistic. All right, so if we've got 180 out of 200 students studied for a test, I'm going to pretend it's higher than that in my brain just because it makes me feel better as a teacher. But out of the 180 students, 172 of those that studied did pass the test. Now let's see if we can identify some of the things that we are looking for here. Well, we don't have a probability of success or failure. Number of trials, what do you think? Because I've got 3 numbers here, and I actually don't need all of them. If we're talking success or failure, I'm guessing we're going to go with success as being the people that passed, failures the people that didn't, which means it's 172 out of 180, which means the 200 here is a little bit on the irrelevant side of things. So I'm going to say that the number of trials is actually 180, so n is 180. And the number of successes then, the r, is going to be 172. All right, we are going to be finding, there we go, a 99% confidence interval. All right, confidence interval for P. And so let's see, other things that we might need to know would include, do we have a p-hat? We could get a p-hat, couldn't we? Because if p-hat is the estimate of the probability of success, and this is how many were successful out of the total, ladies and gentlemen, if I do not know p-hat, I can simply stack r over n and watch my variables. That's an r, that's an n, and if I use this guy right here for guidance, I can use what I've got here to be my probability for success. Borrowing my calculator real quick here, so if we talk with, oh, there it is. Ooh, can you see it? Can you not see it? There we go. So 172 out of 180 is 0.99, so 0.955. I'm going to call it 0.96. So for this problem, my p-hat is going to be approximately 0.96. So I am saying, as my rough estimate to get started, 96% of people that study for the test pass the test. Okay. What else do we need? Well, we know this is probably off from P, but we don't know what P is. But it'd be nice maybe if we had the margin of error. Do we have everything that we need for this formula? We have P, we have Q. Do we have P and Q? Not exactly. We have P hat, which means we could get Q hat. Yeah? If this is the estimate for success, failure's got to be 4%, right? Okay, so basically those guys are going to be our stand-ins for P and Q. We have our sample size at 180. Do we have our critical value? Not exactly, but little mini sketch. There we go. Little mini sketch. Oh, that is hideous. I'm sorry. I can't leave it like that. Sorry, my brain won't let me leave it like that. All right, I can make it better. Okay, I'm happier now. All right, so we are still saying that I've got zeros right here. I'm looking for 99%. That's talking about 99% that is in the middle of this puppy. And so this whole range here, ta-dun, ta-dun, colorful, colorful, colorful. Here's going to be my 99%. Did I make it pretty enough for you? Okay. So I am looking for the z-scores, the critical values that are going to be here and here that would cause me to get this 99% confidence. If there's 99% in the middle, what's in the tails? That would be, well, 1% total. It's a 0.5% at each end. So I could run inverse norm on this. I absolutely could run inverse norm on this and say, hey, if I put a 0.5% in, what's that going to be? And I'm going to tell you right now that the critical score for this thing is a 2.58. So while I could run inverse norm to figure this out, there is often a table available that will give you these exact same values. So 99% is associated with 2.58. And that's going to be positive and negative for the high and the low end for that. All right, so there's my critical value. So I can do this, actually. I can do this. We are talking about margin of error is going to be 2.58 times the square root of, let's see, 0.96 times 0.04 and over 180. All right, so what does that give us? Again, grabbing my calculator here real quick. I keep hitting the wrong numbers, so I'm not going to show it to you yet. Hold on. So 2.58 times the square root of, I'll show it to you in a second, I promise, times 0.04, and then we are dividing it by, yes, yes. Okay, there we go. Ladies and gentlemen, that is it right there. So we are talking 2.58 times the square root of, there's the 0.96 times the 0.04 over the 180, and this is going to be our margin of error, 0.0376. I'm going to call this 0.038. 0.038 is our margin of error. Okay, so based on this idea then, right here, based on this idea, we are saying that if I'm going to find an estimate for p, I'm looking for the ends of the interval. I'm using p hat minus, so the 0.96 minus the margin of error of 0.038 is my low end for my estimate for my p, my proportion of success. And then the high estimate is going to be the 0.96, and that's going to be plus the 0.038. All right, so again, borrowing my friend calculator here, so 0.96, and that's going to be minus 0.038. That gives me on the low end 0.922 is less than p is less than 0.96 plus, I probably should be able to do this in my head, but my brain is a smidge bit toast right now. Yes, 0.998. That makes sense. All right, so that is my low end, that is my high end, but that right there, that is my interval. This is my 99% confidence interval. All right, how do I know that this is meaningful at all? See, there's something here that we just sort of ignored, that we frequently ignore, and I'm going to blame textbooks just because I can. Often, they actually want us to practice our skills in textbooks, and so they set us up for success. But life, when problems just come at you in the world, aren't necessarily all set up for success for you. All of this becomes meaningful only if we have some predictable data, a distribution that is kind of nice. All right, so let's think. What distribution is usually helpful for us? Ah, yes, a normal distribution. Wouldn't it be nice if this was normal? How do we know if this is normal? Well, if you go back in your brains, perhaps, I've talked previously about you can use a normal estimation for binomial under only certain circumstances. And do you remember those circumstances? Hopefully, maybe, kind of, sort of. We said that if we're going to use normal stuff to estimate binomial, which, by the way, we've got z-scores in here, so this is talking, we're kind of assuming this is normal. All right, huge note to self. If you're going to do any of this and have it be meaningful, that means that n times p has to be greater than 5. You've seen that before, right? And n times q has to be greater than 5. So, ladies and gentlemen, everything that we have just done is completely meaningless unless this is true. So should we stop and actually recognize that? We probably should. What would that look like here? That would be 0.96 times 180. Is 0.96 of 180, is that going to be larger than 5? Yes, substantially larger than 5. What if I do 0.04? 0.04 times 180. That's actually going to be 8. Which is small, but still larger than 5, so we are okay. So that means that all of our work here was not in vain, and we can actually use this as a reasonable estimate. So then let's put this to words here, shall we? Because we want to say that we are, go back to this was 99%, 99% confident that the proportion, I hope I can fit this on here, of students who study for tests and pass is between, yay, we're going to make it fit, is between 0.922%, so that'd be 92.2%, and 0.998, which would be 99.8%. All right, so that is our context statement right there. We are 99% confident, because we created a 99% confident interval, the proportion of students who study for tests and then pass them is between 92.2% and 99.8%. So beginning to end, that is what a full problem would look like. I have one more thing that I really want to bring up to you, because oftentimes we are saying, all right, well, I would like to be able to limit my amount of error, and I can do that by choosing an appropriate sample size. we've said that this becomes closer and closer and closer to normal the larger the sample sizes are. So how do I determine an appropriate sample size? We have seen, again, things that are similar to this. And actually, I'm going to leave this here, I think. There we go. But I have two additional formulas for you today. So if we are looking for finding a sample size, I threw the word minimal in here because when we are looking for a sample size, this is the least amount to cause the circumstances that we are trying to get that would be ideal for us. You can always increase your sample size. This is just the minimum requirement for that. All right, if I'm looking for sample size, if I were to take this formula right here and rearrange it a smidge, it might look something like this. Now, I do find this interesting that here, this formula usually uses P and Q, and this formula uses P and 1 minus P. Yeah, but let's just think about that, all right? What is Q? It's the complement of success. So if I take 100% of the things that could happen, I remove the probability of success. What's left is failure. This says P times Q, this says P times Q, but this just doesn't look like it says P times Q. If you'd rather write a Q there, go for it. Again, it's going to be times, we've got the critical value divided by the margin of error squared. So this is just a rearrangement of this formula right here, but this can be used to find your sample size. So if I know what margin of error I'm going to have, I can throw in my estimates for P, I can throw in my critical value, and I can solve to find the sample size that I should have at least. I can always make n larger. Now, here's the other thing, is that I may not know my probability of success. So there has to be another option. What do I do if I need a sample size, but I don't know any of this? All I have is my critical value and my margin of error. How do I proceed? What do I do with this? There is a second formula, ladies and gents. It is right here. All right. And it took me a while to figure out, well, who made this up? Because I can see some similarities here. They both have the critical value divided by the margin of error squared. So what is this? I think I came up with it. I haven't confirmed it, but this should make some sense, right? If I don't have an estimate for P, if I don't know my probability of success, what if I just call it, I have a 50-50 chance? Because that would mean 1/2, 50% for success, 1/2, 50% for failure. What's 1/2 times 1/2? 1/4. Boom, boom, boom. So if I have an estimate for P, I'm going to use this formula. But if I do not have an estimate for P, I'm just going to put a 1/4 right here and then run the same thing. So be aware of your circumstances. If you are looking for sample size, if you are looking for N, this is an option if you have P, if you have a preliminary estimate. This is an option for N if you do not. And if you are looking at a problem that has sigma in it someplace, you are in the wrong place. Notice there's no sigmas here anywhere. You need to go back to our stuff that was dealing with mu instead of P. This is binomial and binomial only at the moment. All right, is that it? Oh, that's almost it. All right, so a couple pointers and then I promise to be done with you. N has got to be a whole number for sample size, so please keep in mind that you do want to round up if N comes out as a decimal, which it probably will. And then specifically, because in order to do all this stuff, we said that we absolutely have to have an NP and an NQ that's greater than 5. All right, so if you do all this lovely stuff and you end up with an N value that's too small, keep increasing it. Make sure that NP and NQ are greater than 5. Again, we can always increase the sample size. This is just the minimum requirements for that. All right, so eyes open, pay attention to details, and, ooh, 2 seconds. You're going to want to see this. I'm sorry. I forgot I had this set up. Hey guys, check this out. So calculator friend, yes? It is really, really important that we know what has been happening and understand it from a conceptual level. Calculator can help us out here. Everything fun and exciting is in the menu. Briefly. Statistics. Let's go statistics, yes. Oops, there we go. And we are still working in confidence intervals. But we've done Z intervals when we're looking for mu and we know sigma. We've done T intervals when we're looking for mu and we don't know sigma. This is a proportion stuff, but still using Z scores. So here we go. 1 prop Z interval is our friend. 1 prop Z interval. Calculator might use X instead of R. So if I type in my number of successes, from previously, we said we had 102 successes out of 180 trials, out of 180, there we go. And we did a 99% confidence interval. So I'm just going to change that to a 9 and tell it okay. And lo and behold, ladies and gents, all right, what we are seeing here is very similar to what we produced on our paper earlier, talking about calculator, by the way, if it's between me and my formulas in the calculator is going to be more exact. But we said something close to 92% on the low end, a little over 99% on the high end. We'd use We used a rounded estimate for p hat, remember, which is why their answer is going to be more specific than ours, because we called this 0.96. There's our margin of error. There we go. So everything you need to know is also in the calculator, but understand what is happening, because otherwise you're lost. All right. All right. Thanks, guys. Have fun. Enjoy.